All right, welcome. So today we are jumping right into the pretty incredible world of electrochemistry. This is the science that explains how chemical reactions can actually make electricity and how electricity can make chemical reactions happen. It's this really cool two-way street that, believe it or not, you use every single day.
Okay, so have you ever stopped to think about this? Your phone battery dies. That's a chemical reaction finishing its job. Then you plug it into the wall, and somehow electricity reverses the whole process. I mean, how does that even work? That's the big mystery we're going to unravel today.
All right, first up, we've got the power generating side of things. This is the voltaic cell, which you might also hear called a galvanic cell. This is all about grabbing energy from reactions that, well, want to happen all on their own.
So what is it really? A voltaic cell is a super clever setup. It takes the energy from what's called a spontaneous redox reaction, and hey, don't let the jargon scare you. That just means a chemical reaction that happens all by itself, no pushing required. It captures that energy and turns it into a flow of electrons, which is, you guessed it, electricity.
And this is the perfect way to think about it. You don't have to push the ball, right? It just rolls downhill, releasing energy as it goes. That's exactly what's happening in a voltaic cell. The reaction just goes, giving off energy that we can put to work.
Okay, so how does this actually work? Let's take a look at the classic Daniell cell. You've got two sides. On one side, the zinc anode is literally giving away electrons. Those electrons then travel through a wire, maybe lighting up a bulb along the way, over to the other side. There, copper ions at the cathode are waiting to grab them. And that salt bridge in the middle, absolutely crucial. It keeps the charges balanced so the whole thing doesn't just stop. It's a really elegant system.
Okay, so getting power from a reaction that wants to happen, that's half the story. But what about the ones that, well, don't? This is where we meet the other side of the street, electrolytic cells. These use power to force a chemical change that would never happen on its own. And the difference between the two is just wow. You've got the voltaic cell turning chemical energy into electricity, just like that. And then the electrolytic cell does the complete opposite. It needs power from the outside to make a reaction happen, turning electrical energy back into chemical energy. They're literally mirror images of each other.
So remember our ball rolling downhill? That was the voltaic cell. Well, the electrolytic cell is you having to push that ball all the way back up the hill. It won't go by itself. It takes effort. It takes an input of energy to make it happen.
Okay, now one of the things that trips everyone up in electrochemistry is the charges on the electrodes, because they flip depending on the cell. But for electrolytic cells, there's this amazing little trick. Just remember to panic. P-A-N-I-C. Positive is anode, negative is cathode. So simple, and it works every time.
So, knowing the charges is a good start. But, things get a little messy in the real world. It's one thing if you've got a simple molten salt. But what happens when you've got a whole soup of different ions in a solution all fighting for the same spot at an electrode? This is where we get into something called selective discharge.
So here's the big question. When there's more than one option, how does the cell choose which one gets to react? If you've got copper ions and water molecules hanging out near the cathode, which one actually gets the electrons? There's got to be some kind of rule, right?
And there is. It all comes down to this thing called electrode potential, or E0. The easiest way to think about it is like a leaderboard. It basically tells you how badly something wants to gain electrons, or in chemistry terms, how easily it can be reduced. Okay, let's look at the numbers. At the cathode, that's where things gain electrons, the rule is simple. The one with the more positive number wins. So, copper has a potential of plus 0.34 volts, while water is way down at minus 0.83. It's not even a close fight. The copper ions get the electrons every time.
But, and there's always a but in science, isn't there? Electrode potential isn't the whole story. When the race is really, really close, something else can tip the scales and act as a tiebreaker. Concentration.
Let's look at what happens at the anode with water and chloride ions. Check out that difference in their potentials. It's only 0.13 volts. That is tiny. We're talking about a chemical photo finish here.
And because that gap is so incredibly narrow, if you use a really concentrated solution, the sheer number of chloride ions, just by being everywhere, can basically elbow their way to the front of the line. So instead of getting oxygen from the water, you get chlorine gas, all because of concentration.
Okay, so that's the science behind it. But what does this have to do with, well, anything? Turns out, this stuff is happening all around you in all sorts of huge industries, from making car parts to making jewelry.
I mean, electrolysis is a total workhorse for industry. You know those cool colored aluminum window frames? That's anodizing. That super pure copper we need for pretty much every wire on the planet? Yep, made this way. Shiny chrome on a car? Gold plating on jewelry? That's electroplating. It's even how we get super important metals like aluminum out of the ground.
Okay, let's zoom in on that copper refining for a second. So you take this big, dirty slab of copper and make it the anode. You run a current, and that anode starts to dissolve. The pure copper ions travel across and plate themselves onto the cathode, building up a sheet of almost 100% pure copper. And all the gunk, all the impurities, get left behind.
So what happens to all that gunk? Well, the stuff that's less reactive, think gold, silver, they don't dissolve. They just fall off. And they collect at the bottom of the tank in this gross-sounding stuff called anode sludge.
And here is the absolute best part. That sludge isn't garbage, it's treasure. It is literally a gold mine and a silver mine and a platinum mine. The waste from refining copper is actually a huge source of the world's precious metals. How cool is that?
All right, so let's wrap this all up in a neat little bow. The voltaic cell is your downhill reaction, making electricity all on its own, with a negative anode. The electrolytic cell is the uphill climb. It uses electricity to force a reaction, and its anode is positive. And for that, don't forget panic to keep it all straight.
And that brings us full circle, right back to your phone. The next time you see your battery is getting low and you plug it in, you'll know exactly what's going on inside. You're not just filling it up. You are using electricity to force a chemical reaction to run backwards. You are literally pushing that chemical ball back up the hill so it's ready to roll down again and power your day.